Good morning, good evening, honorable ladies and gentlemen. It's an honor to have the opportunity to participate in NATI's 22 conference. On this very good occasion, I'd like to present our research paper entitled Mechanical Energy Minimization EFV Mounted Base Station Path Plan for Safety Communication. For the content of this presentation, we will start by giving you a very short introduction about our work. We will talk about our motivation to formulate our problem, and we will propose solutions ACO and Metropolis-hasting. After we will discuss the results, and finally, we will conclude this presentation by conclusion and some perspectives. Natural disasters interrupt the existing communication infrastructure or move large population overburden what remain of the communication infrastructure. People in this situation need direction, guidance, updates on the actual situation, and communicate of their current location to emergency teams. In an ideal world, users need to be able to communicate with each other directly, despite the lack of communication infrastructure, which is common in disaster situations. It is therefore essential to develop innovative solutions and approaches to replace or integrate existing communication infrastructure for the advantage of the damaged population and first responders. EIV-aided communication is presently receiving a fair share of attention from researchers due to its low cost, quick, and flexible deployment. UAV-mounted base stations are distributed to supply communication coverage in the damaged areas where users could be grouped. We design energy minimization trajectory for the feeder EIV to visit all the EIV base stations, the relay EIV, and return to the docking station. We will compare the ACO and method MCMC Markov chain Monte Carlo solutions to find a path that can minimize the energy requirement of our feeder EIV supplied to charge the EIV's base station batteries. And finally, we will see that the numerical analysis validates our ACO design's superiority over the algorithms in our Metropolis-hasting and algorithm and genetic algorithm experiments. The mission of our feeder EIV is to find the optimal trajectory with the less propulsion energy requirements. To know more about propulsion energy, we must first define two types of energy consumption that the EIV can consume. On the one hand, consumption is linked to communication, which is used for various communication functions such as signal transmission, calculation, and signal processing. On the other hand, we found the energy of propulsion. This energy corresponds to the consumption of mechanical energy, namely the movement of the EIV. If the EIV fly straight and when the EIV makes a turn, and finally we add the consumption of the hardware. Assuming that the n EIV base stations are randomly distributed in the relevant areas with the least airspace separation of 2r between two EIV base stations and the high of h for the feeder EIV. The propulsion energy consumption required for straight flight during a flight time t is defined by equation 1. The propulsion energy consumption required for the turn during the flight time t is defined by equation 2. The energy levels of the hovering UAV and hardware denoted by A half and A hard can be expressed respectively by equations 3 and 4. Now, trying to mathematically model our problem by using the fitness function, which is equal to the fraction of the summation of the energies consumed by the hardware as well as the hardware. The first optimization method used is ant colony optimization. Before moving on to briefly explain the basis of these phases, we must know some keywords. First of all, we have a group of ants, K, which designated as the possible solutions. The population of a group of ants, N, and surface space, LBEB, which groups together all the possible solutions. We have crew the surface space by the step size H, pheromone trial, scale parameter, and evaporation rates. Four phases are considered in ACO: input, initialization. We initialize all discrete value m of design variable with equal amounts of pheromone. The principle of the algorithm is summarized in two loops. The first loop found the probability of selecting the discrete value of the design variable, which is equal to the pheromone of each ant with respect to the summation of the pheromones of the others, and determine the zones of cumulative probability related to different discrete value according to its probability. The second loop generates a random number R, founding the corresponding discrete value, and evaluate the fitness function f of each ant. From the evaluation, one has determined the best and the bad fitness function value of discrete among the ants. Based on the fitness value, we will update the best paths by this equation and the other by this equation. The second method used in our work is MCMC, Monte Carlo Markov chain, using the Metropolis-hasting algorithm. Let us note by Sn the set of the trajectories that the feeder UAV can cover. A trajectory is of the following form. In fact, a vector containing the ordered set of UAVBSs that the feeder UAV visits. Thus, the energy consumed of a trajectory is given by the following relation, and the function to be minimized is therefore the function f. Let f be a continuous function with a value Sn. The Metropolis-hasting algorithm is as follows. Step 0. Choose a transition core Q. Choose a random path, trajectory 0, and define a maximum number of iterations. Step 1. Simulate trajectory 1 according to the transition Q of trajectory 1 by trajectory 0. Step 2. Calculate the Metropolis-hasting ratio. Step 3. Draw U according to a normal distribution on 0, 1. If U less than or equal to ratio of trajectory 1 by trajectory 0, put trajectory 0 equal trajectory 1. Else, conserve trajectory 0. Repeat iterations max times algorithm. The function f corresponds to the stationary law of the Markov chain that we want to simulate by this algorithm. We take this f. By choosing this function, we assume the convergence of the algorithm to the minimum. In our approach, we will choose a symmetrical transition core. That means that the transition of trajectory 1 by trajectory 0 equal to transition of trajectory 0 by trajectory 1. The Metropolis has a report that becomes as follows. We illustrate the UAV's mounted base station topology and optimal fly trajectory for ACO and Metropolis-hasting respectively. The green dashed segment represents the ideal path proposed by the MCMC method, and the red dashed ones indicate the optimal trajectory design obtained by ACO. As we can see in the figure on the left, as the speed of the feeder UAV increases, the energy requirements of all the algorithms decrease until they reach a minimal speed of 30 meters by second, at which point they start again to speed up again. This behavior is related to parasitic overshoot drag and induced drag, and is considered with energy level of the aircraft. At a high rate of UAV feeder, we can observe that the suggested ECO design outperforms the algorithm based on genetic algorithm and the proposed MCMC algorithm by more than 38% and 48% respectively. And in the figure to the right, all algorithm power requirements increase with the number of UAV base stations as expected. This is due to the growth in flight time and the number of turns required for the feeder UAV to reach all UAV base stations as the number of UAV base stations increases. As conclusion, we compared a trajectory design based on the ACO algorithm and the Metropolis-hasting algorithm for moving the feeder UAV to charge the batteries of UAV base station, deployed around a disaster area and returning to a docking station. To calculate the energy requirement of the feeder UAV, the design on the path consider both the hover and the hardware. Finally, in terms of total energy requirement, simulation results show that the suggested solution outperformed the path algorithm based on genetic algorithm. As future work, we should consider extending our proposal with a swarm of UAV feeders, and the paths should be constructed to be dynamic, dependent on the problem parameter, such as residual energy and accessibility of the area. It's all about my presentation. Thank you for your attention.